All right, guys, it's that time. Good morning. Let's get started. So today we're moving on and talking about graphing some fraction things. Where their graphs look like they're actually pretty straightforward. You got to get a basic shape down, and of course, know the same normal things about stretches and shifts and things like that. But it's not going to be that complicated. I don't think it'll be that heavy of a lesson. Nice break from the last couple of ones that were pretty tedious with all the mechanics of adding, subtracting, multiplying, dividing fractions. So before we get started on that, of course, we're going to warm up and we're going to practice those skills we just discussed and adding, subtracting fractions. So here we go. Number one, we have our fraction x squared. We got three fractions. Oh no, that's all right. Well, if I have to add three fractions, I'll get them all to have the same denominator, not all their tops together. But I wonder why they gave us these particular denominators. This one right here is flat out by definition a difference of squares. Would you agree? It's something squared minus something else squared. And you got to remember that that's a great one to know for life. You know, it comes up all the dang time when you're factoring things. It's the first one plus the second one and times the first one minus the second one. So we can actually factor this x squared minus x squared minus y squared into an x plus y and an x minus y. And you see when you do that, look what was secretly inside of that denominator. Things that were in the other denominators, correct? Great. So, well, let's see. Shoot. This one's got two things on bottom, though, right? Well, one's x plus y and one's x minus y. So my goal is to get them all to have an x plus y and an x minus y on the bottom. The second fraction here already has an x plus y on the bottom, correct? So we'll put an x minus y on the top and bottom to fulfill the prophecy. X plus y, x minus y. There we go. And now that has the same bottom. And similarly, for the last one, it already had an x minus y. So I'd like to give that an x plus y to complete the set. So we'll put an x plus y on top, which means I got to put an x plus y on bottom. And that's why you want to always factor your bottoms, because secretly things inside of them, including numbers, if you have a 15 and a 35 or something like that, you might want to factor those down and see what numbers are buried in them. Might have something in common, might make your life a little bit easier. Okay, so now all we got to do is actually add all and subtract all these tops and put it over the bottom. Bottom stays the same, so x plus y over x minus y. What do we got to play with up here? Well, let's just distribute. How about that? We'll clean it up in a second. This first one had an x squared plus y squared, so x squared plus y squared. The second one had these two things multiplied together. And I think you might want to actually distribute these out. Probably maybe distribute out the tops, never the bottoms. There's no point to distribute out the bottoms, but the top. Let's see what we get when we distribute this out. Y times x, or I like to write things in alphabetical order. I'll write x times y. And then y times negative y is negative y squared. So there's the second fractions thing added. And the third one's got to be careful with subtraction ones. Remember what I keep harping on. You have to subtract all of these terms, correct? All of them. Well, what terms are here? There's an x squared and an xy. Would you agree? So I need to subtract both x squared and xy from this particular expression. Well, shoot, that's kind of cute. Look at this thing. What happens on the top? This is a surprise to me. I didn't know what this problem was going to be. Doesn't this x squared and this x squared cancel? Well, shoot, then that's nothing. And this y squared and this minus y squared cancel, don't they? And this xy and this minus xy cancel. So they all cancel out. Now, what's on top when they're gone? Is it? Because what were you doing on top? You weren't dividing through by the bottoms or anything, were you? What's x squared minus x squared? 0, right? What's y squared minus y squared? 0. What's xy minus xy? 0. So what's the whole top turn into? It's a 0, actually. Things only turn into ones when they cancel with the bottom. If you have like a 5 on top and a 5 on bottom, they cancel and leave a 1 because 5 divided by 5 is 1. But in this case, they all just turn into a 0 on top. And 0 divided by anything is 0. So apparently this entire expression, as ugly as it was, simplified down to nothing. That's weird, isn't it? That was a good problem. I like that. It surprised me. I like that. Turned out all nice and clean. Okay, moving right along. Number 2, slightly easier. It's only got 2 fractions. 1 over x squared plus 2x plus 1, which is just screaming to be factored. And x over x plus 1. So how does x squared plus 2x plus 1 factor? Yeah, 1 and 1. Yeah, x plus 1 and another x plus 1. Well, that fraction has 2x plus 1s on the bottom. The other fraction only has 1x plus 1, correct? let's fix this issue by giving this second fraction another x plus 1. So if you multiply the top by x plus 1 and the bottom by x plus 1, then you have this, and we're pretty much got a common denominator ready to go. So of course the bottoms stay the same. That's how you add fractions. And you only have the tops. I think we can do it all in one shot here. Let's see what we do have up top. There's a 1. You also see there's an x squared and an x. Yeah, so putting that in the right order, there's an x squared, there's an x, and there's a 1. And I should look at that top again and ask myself, maybe I could factor it again, but it doesn't factor. There's no numbers that multiply to be 1 and add to be 1. There's no such thing. So those have complex or imaginary kind of things, and we're not going to go down that road, so we're good on that. Questions on 2? All right, sounds like we're making some sense. And 3 is pretty much straightforward too. This one says 5 over x plus 3. And you are subtracting 1 over x squared minus 9. And the x squared minus 9, that's another difference of squares. It might not look like 9 is something squared, but we know it is. It's 3 squared, correct? So there's 2 ways to do it. Of course, you could say it's a difference of squared. You could call it x squared minus 3 squared, couldn't you? Then you could factor in x plus 3 and x minus 3. Or you can just think it through. There is no middle term, correct? So it's really 0, isn't it? And the 2 numbers I would multiply to be not -9 and add to be 0 would be positive 3 and negative 3. So no matter how you look at it, if you just look at normal factoring, or if you want to use some equation that's on the board, either way, you'll get to x plus 3 and x minus 3. And then again, you look at them and you ask yourself, why are the bottoms not the same? Well, they both got an x plus 3, but this guy's got an x minus 3. So let's give this guy an x minus 3 on the top and the bottom to make it all work out. So this one will be 5 times all of x minus 3 over the x plus 3 that was already there, and the x minus 3 I'm putting on bottom. And we're going to leave the other one alone because it already had the desired denominator. And now all I got to do is actually subtract the tops, right? Bottom stays the same. I'll go ahead and write the bottom. Just get that tediousness out of the way. So there's an x plus 3 and x minus 3 on bottom. On the top, all together, let's see what we have. If you distribute the 5 in, you'd have a 5x. And also from the distribution of the 5 times -3 is -15, right? But while we're at it, we're subtracting 1. And -15 minus 1 is -16. And I take a step back. Can I factor any more? No, nothing goes into 5 and 16. There's nothing I can do with that. Nothing cancels. So we're done. And that's all I can do for that particular problem. How do you guys feel about the fractions? Okay, decent? Decent. I know it's a lot. It's a hassle. I get that. On the test, I will not give you anything with x's and y's. I'll try to keep it relatively straightforward. Maybe number 3 and number 2 might be the speed of your test or something like that. It's not going to be insanely complicated with like x's and y's and b's, z's, and w's and all kinds of thousands of layers floating around. I just want you to be able to do this with x's, and if you can, you'll be just fine. Okay, LGs today. We're going to learn how to graph reciprocal functions. Sounds fancy. Basically, reciprocal is what it sounds like. It's a fraction. It's something flipped. The most basic function in math is f of x is x. Boring. So the most basic fraction you could take is taking x and flipping it. And if you just take x and flip it, x is really x over 1. You get 1 over x. And 1 over x, I've kind of previewed that in the beginning of the unit. But that will be our topic today, called the reciprocal function. It's 1 over x flipped. And our fancy word for flipped is reciprocal. So it's a reciprocal function for that reason. 9.2 is due, of course. So by 3 o'clock, that should be turned in. And then there's the new one, 9.3. You have plenty of time on it. It's really not that complicated either. So I hopefully we go pretty easily for you. Nice little break. Not due till Tuesday either. So you got work time on Monday. You got the weekend also, and it's relatively straightforward. So you should have no problem getting 9.3 taken care of. If you're doing it on the online textbook, it's on page 473. Numbers 1 through 6, 13 through 16, 23 through 29. Sounds like a lot, but they go pretty quickly because they're just straightforward graphing things. And then just 31 through 39 odd. Might want to get your calculators out too, because it's a graphing day, so we're going to graph things, and never a bad idea to practice plugging things into our calculator and things like that. Again, this is 9.3 called graphing reciprocal functions, reciprocal functions. And before I even show you the graph, maybe I want to just take a second to tell you why the graph might be the way it is. So I want you to go to your calculator, and I want you to just go to your home screen. We're not going to graph anything right now. We're just going to go to our home screen. And we're obsessed with things. You don't have to type this in, because it doesn't make any sense. By the way, your calculator doesn't know what x is. If you keep relying on x being a number, I mean, your calculator has something stored as x. So whenever you hit the x button, it doesn't represent a variable, it represents some number stored in your calculator. My calculator apparently thinks x is 10. So it's not. So by the way, don't be ever just typing in, well, I typed in x squared in my calculator and it said it was 4. Well, what's your calculator think x is? X is just a number. Anyway, we're going to be studying things like 1 over x today. Now, to show you what the graph does, here's what I want you to do. I want you to take 1 over different numbers. And what can you not divide by in math? That's right, 0. So I want to show you why you can't divide by 0, and we're going to approach 0 on the bottom. We're going to start kind of far away from 0. The first thing we're going to divide by is just 1. And obviously, 1 divided by 1 is 1, right? Well, let's get closer to 0. Let's divide by something pretty small, like 0.1 or something like that. And if you do 1 divided by 0.1, you get 10. And remember what division is asking you. It's asking you how many of the things on the bottom does it take to get to the thing on top. So how many 0.1s does it take to get to a whole 1? It needs 10, because by definition, 0.1 is a tenth. If you divide by 0.01, a hundredth, how many hundredths does it take to make a whole? 100 does. And as you get closer and closer to 0, say I get a really tiny number, just whatever you want, what happens to the numbers? They just get bigger and bigger and bigger. And the closer you get to dividing by 0, let's see here. I'll get really, 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 really small. The bigger, that's so big that my calculator puts in scientific notation. 1 times 10 to the 15th. That means 1 with 15 zeros out there. That's a huge number. What happens when you divide by negative numbers that get close to 0? I'll start off with like -1. Well, it's -1. If you divide by -0.1, you get -10. It's the same pattern. It's just the only difference is that there's going to be a negative. So when you approach 0, either from the left or from the right, this thing either gets really, really big to infinity or goes down really, really far to negative infinity. Hence the reciprocal function. I'll show you the graph in just a second, but here's the definition right here at first. A reciprocal function is something of this form, n over b minus x. And the key thing here is that it's nothing special. The n on top is just a number, so it could be like 4 over something or 5 over something. That's not the interesting part. What's interesting is that the bottom is some kind of linear expression. And by linear, I mean just x's and no x squared. So it could be x plus 2, it could be 5x, it could be 7x minus 3, but no x squareds, no square roots, no nothing. It's just got an x on the bottom, basically, and some numbers. That's all a reciprocal function is. Now, I think what's going to happen here is this graph does a lot more justice to what this is saying than I am. Take a minute and jot down this graph. This is called your reciprocal function. We'll graph that on our calculator in just a second. This is a graph of what 1 over x looks like. And this is your parent function. This is the thing we're going to take and stretch and shift and move around and do all kinds of things to. This is the main thing you need to understand. It's the most basic version of a reciprocal function. The number on top is just a 1, and the variable on the bottom is a x. And as we just kind of investigated, if the number on the bottom gets closer and closer to 0, then it just gets bigger and bigger and bigger. That's why it blows up right there. And that's the main thing I want you to take away from this lesson. Whenever the bottom is 0, your graph blows up. That's the main thing. Whenever the bottom equals 0, your graph blows up. If you come in from one way, it blows up to positive infinity. If you come into 0 from the other way, it goes down to negative infinity. And that's what you need to recall right there for that. So there's 1 over x. Fair on that? Very good. Good to know there's also a couple of asymptotes associated with this. I'll go off script and tell you what I think is the most important thing. It's mostly what the same thing as this is. By the way, this shape is called a hyperbola. You don't need to know that, but just in case you want to know, that's what a hyperbolic kind of thing looks like. What I really want you to know about this graph is what it already said, but I want you to start getting the habit of drawing me some dashed lines. Dashed lines for asymptotes. It wasn't shown on that graph, and that's okay. This graph of 1 over x blows up at 0 because for this particular graph, that's what makes the bottom equal to 0. So draw an asymptote like that. By the way, you also should know that it also has a horizontal asymptote. It levels off on both ends to 0, which is really, really cute. So same shape as before, it's going to hug this axis. It's going to come down, and it's going to hug this axis. And vice versa over here. So this is what you should know for a reciprocal function. Looks like that, which you already jotted down. Of course, for any function, you should probably know what the domain and stuff is, but I really don't want to, specific just to this particular function. The domain is everything except for 0, because that's where things kind of fall apart precisely. Now, if I give you another fraction, if there's like say there was an x plus 2 on bottom, what would make that 0? -2 would, wouldn't it? So you'd say it's everything except for -2, and it wouldn't blow up at 0, blow up at -2. So the graph blows up at whatever makes the bottom equal to 0. The range by default is all the numbers except for 0 also. It goes all the way from -infinity up to 0. It doesn't touch it. And then everything from 0 up to infinity is fine after that. But again, there could be a shift or a stretch or something like that, and then maybe that moves things around or something like that, but we'll talk about that in a second too. It shows it on both ends, but just to be complete, let's talk about the end behavior. It's been a while since we've done this stuff. Limit as x goes to -infinity, that just means it's going to the left, right? As you go to the left, this thing levels off closer and closer to 0. And similarly, as you go to the right, this thing also levels off to 0. So those are the things that should be in your mind with the reciprocal function right there. Or anything we're studying in this entire unit. Most of the graphs are going to kind of look like that and level off to something on the ends. Expect it to blow up, explode, wherever the bottom equals 0. That's the heart of today. When does the bottom equal 0? Okay, so let's do an example of what a graph of this might look like. Here we go. We got g of x equals 2 over x minus 7. This is a reciprocal function. It's some number on top divided by something that's linear on bottom. Linear just has x's, no x squareds, no x cubes, no nothing. So the way you always start this analysis is what makes the bottom 0? What is it not allowed to be, guys? 7 would be bad. So I know right off the bat, well, let's just get the domain over with. I can plug in anything into this equation except for 7. When they ask you for the excluded values, what they're asking you for is what values can it not be? What values are excluded? And the only one is 7. So in a roundabout way, they're asking you when does the bottom equal 0? The graph, like I said, will blow up at 7. So over at x is 7, 1, 2, 3, 4, 5, 6, 7, there will always be this vertical asymptote. I do want you to get in the habit of labeling them too. They're lines. Lines have equations. If over there, everywhere on that line, x is 7, then the equation of that line is x equals 7. Now, normal business too, I want you to look at this and I want you to tell me if there's any other differences between what we know and this thing. Well, the x was replaced with x minus 7, correct? Now, we already took care of that actually. What does replacing x with x minus 7 do? It shifts everything to the right by 7. Well, look at this shape. Where was this at? It was at 0, wasn't it? If you shift it over 7, where is it? At 7, correct? So you don't need to worry about that because you can just think about when the bottom is equal to 0. Is there any other significant difference to this? There's a 2 on top instead of a 1, but there's no negatives floating around. Would you agree? No reflections, no weird stuff. I don't see anything plus on the end either, do you? So I don't think it's going to move up and down either. So where did it used to level off at? 0, right? And we didn't move up and down, did we? So it's still going to level off at y equals 0 right there. And then since there were no negatives in front of my x's and no negatives in front of my equation, nothing reflecting, it's the exact same shape. Only difference is I need to hug this asymptote right here. So it looks something like that-ish. That's approximately what this graph would look like if I chose to graph it. Just to check, you could do it on your calculator. Why don't you do it on your calculator real quick and see if you see something like this. If you don't see something like that, this is what we need to talk about real quick, because I anticipate maybe not typing this in our calculator correctly. I don't know. How many people are typing that in? You were going to get the wrong thing. What is wrong with what I'm typing in right now? Anybody know? I need parentheses on the bottom. That's exactly what I was worried about right here, because your calculator follows PEMDAS. If you type it exactly like it looks right here, it's going to do 2 divided by x only. And then after it's done with that, it's going to subtract 7. So yes, whenever you are dividing by things, make sure you put them in parentheses. That is super, super important. So it's 2 divided by all of x minus 7. That's exactly why I wanted to run the calculator thing real quick. And if you type that in, here it comes. It goes down, it comes back up, and guess where it blows up at? 7, because that's what makes the bottom equal to 0. How about this one down here? Let's try this one. C. Ooh. It's got a negative 5 on top. What do you think the negative on top does? Any guesses? It does do something to the graph. Thoughts? What do negatives usually do? They usually reflect things, don't they? This is no different. In fact, as a little side comment real quick, maybe I should discuss all the transformations that are possible really quickly, just so you have some kind of quick guide for yourself. Let's say you start with this, 1 over x. How do you vertically stretch a function? You multiply it by something, correct? Well, if I take this and I multiply by, say, a number a is a over 1, correct? And how do you multiply fractions? Straight across. So multiplying the whole thing by a is the same thing as having a number on top that is a. So if you see a number on top, it actually represents your vertical stretch, like always. You multiply something by a number. Whenever you multiply a fraction by a number, you can just put that number on top. So the number on top represents your vertical stretch. And if it happens to be negative, of course, it could be a vertical reflection. Same old business, right? And if you replace your x's with stuff, okay, let's replace my x with x plus, I don't know, k, or now we usually use h, don't we? Then if I replace my x with x plus something, then it's a horizontal shift, right? If I multiply my x's by something, say b, then that's a horizontal stretch. And if it happens to be negative, it's a horizontal reflection. And of course, if you add something to the end, it's a vertical shift. So here's your little template. If you want to jot that down for what everything in an equation might stand for, I'd prefer you don't have to memorize that at this point. At this point, we should know that if I just take my x's times something, it's a horizontal stretch or reflection. If I add something to my x, then it's a horizontal shift. If I have something on the end, it moves it up and down. The only thing that really probably I could understand not making sense so far is just the number on top. The number on top represents your vertical stretch or your vertical reflection. So keep that in mind. And then back to the problem. What's on top? There's a negative 5, right? The 5 would therefore represent a vertical stretch. Again, is it easy to draw stretches? Not really. So I'm not going to worry about that too much. But there is a negative, and I better worry about that. Because what happens to that? That's a vertical reflection. So in my mind, the new shape I need to have understood is this one, 1 over x, right? That's 1 over x. So this one won't look exactly like that. It's going to look like it vertically reflected. This won't be down here. It'll be up there. This won't be up here. It'll be down there. So far, just by looking at this thing, I'm kind of thinking it looks more like that than the original. Are you buying that so far? Okay. That's the general shape. But again, when does this thing blow up? It's not always at 0. It's whatever makes the bottom equal to 0, correct? So off to the side real quick, when does 3x plus 4 equal 0? And if you move a couple things around real quick, it's a weird answer, but apparently the thing that is bad, that should be excluded from the domain, that should not be included where this entire thing falls apart and blows up, is -4/3. Was there any number on the end, any plus k's, anything on the end like this? Nope, no vertical stuff moved up and down. So I'm going to take this shape I have in my mind. It doesn't blow up at 0, it blows up at -4/3. That's a little past -1, so right here-ish. X equals -4/3. That's where my graph will explode this time. As you already pointed out, there were no vertical shifts, nothing screwed up and down. So since they normally level off at 0, they're still going to level off at 0. There's my crisscross shape. That's what you're always going to have on these kind of things. There's always going to be a crisscross kind of thing going on. Not to be confused with the 80s rap group. Crisscross will make it jump. And it looks like this, right? So we just fill in the gap now. So it looks like that because it was reflected. And you have your calculator too, correct? So please graph it after you think it through. Don't just rely on your calculator. That's how we don't learn. That's how we have bad grades and things like that. Try to do it with your mind first. Verify it with your calculator. And I guarantee it looks something like that. Cool? Okay. That's the basics of it. Let's see what other examples they got for us today or other topics. Let's just see if you know when things are undefined. When does the bottom equal to 0? So here's a few examples for you, a few functions. 9/17x. The bottom is 17x. When does 17x equal 0? And don't tell me it's 17. 17 times x is 0.
0/17.
Which would be, so this is undefined at 0. A lot of times kids will see that 17, they'll just say, oh, 17 or something like that. Nope. 17 times 0 is 0, so you're right. The undefined value is when x is 0. How about B? Pretty obvious. When is that bottom 0? 11, I would agree. And C? Ooh, I don't know. Not so obvious, is it? It is -4. Don't be afraid to go off to the side, though, and step out a little equation and solve it. You are correct, it is -4. But if it's too cumbersome for you and you're not sure, please just go off to the side, set it equal to 0, do a couple quick little steps, and solve it. All right, how about this thing? Let's do the whole thing. Consider this function. Identify key features, blah, blah, blah. We're just going to do the same thing we always do. We're going to graph it. So this thing, we got ourselves a 1/2x minus 5. Ooh. And on the end, a +2. So before we get too lost in the weeds, what shape will it have? Do you see any reflections? I don't see any reflections. Reflections would either come from the number on top, that's the vertical reflection, but it's positive, correct? Or the number in front of the x, but that's also positive, correct? So there's no reflections. So this is basically going to look like that. Scoot it around a little bit somewhere. Well, where's it going to blow up at? Wherever the bottom is equal to. Let's get that over with. Can you tell me what it is in your mind? It is 5/2. That's exactly right. For the record, I'll do it because I'm recording it. If you set this equal to 0, then yes, you'd move the 5 over and divide by the 2, and that's exactly right. 5/2 would make the bottom 0, so that's bad. You don't want 5/2. Your domain would be everything from -infinity until 5/2 and skip over it, and everything from 5/2 to infinity. But then right off the bat, we know this thing's going to blow up at 5/2, which is 2.5. So halfway between 2 and 3, at 5/2, this graph's going to explode. What's the horizontal asymptote going to be? It's not going to be 0 this time. It's going to be 2, exactly. You got a +2 on the end, right? That scoots things up by 2. If it usually levels off at 0, it's going to level off up here too. So right there at y equals 2 will be my horizontal asymptote. And then we said the shape didn't change. It's the normal shape. So we'll just kind of hug these little crisscrossy things. Something like that. And that would be roughly what this particular graph would look like. See, not that bad today, is it? Nah, you just got to know what these things are talking about and you'll be just fine. And then they go into exactly what I talked about, their reflections and all that stuff. You don't need to worry about that. There's 2 more examples. Let's do them because they take like 2 minutes each and then we'll call it a day. So how about this one? G of x is -4. Oop, right off the bat, what's that -4 tell you? It's going to be a vertical reflection, dang right. So this shape is going to be flipped from what we are used to. So since it's flipped, and again, going back to what we know, here's the default parent function that I know, right? Reciprocal function, brand new one today. That's what I have in my mind. Tattoo that in your soul. That's the shape. But you did say there's a -4 on top, so that's going to reflect it. So when you reflect that thing, it's going to turn into that. Do you buy in that? Kind of looks like that. Okay, it doesn't curve back down. I kind of got a little sloppy there. Okay, there's the shape. Can you tell me by looking at it where it's going to blow up at? -1. Whatever makes the bottom equal to 0. So right here at x equals -1, we're expecting this thing to blow up. The numbers are going to get bigger and bigger and bigger as I come in from either side because the bottom's getting closer and closer to 0. And then the -2 on the end just moves things down too, right? So it's not going to level off at 0. It's going to level off down here at -2. So there's y equals -2. And then since we already discussed the fact that the shape is going to be more like this than normal because it got reflected, just got to hug them. And that's kind of why you want to draw these lines anyway. You want to make sure you don't cross them. It's an asymptote. It should approach this line, but not actually cross it. So if on your test, I give you this equation, and you have it going up here and leveling off, that's not going to cut it, is it? Because it needs to level off at -2 in this particular case. Questions on that one? All right, one more for good measure. Let's see if you can do it. You try this on your own. Try to graph this one. See if you know what it looks like. Think about reflections. Blows up when the bottom is 0. Makes a vertical asymptote there. You should be noticing by the structure of it that there's just a 1 on top. There's not a -1. There's not a -x. There's no reflections involved. It's the normal shape, correct? Did you get a graph like something that looks like it's on the board? Should have got that. Yep. Blows up at 1 because that's what makes the bottom 0, correct? And the 3 on the end shifted things up 3, so the horizontal aspect wasn't at 0. It was up at 3. And that's pretty much it for the day. Not that bad, is it? Good. I'm glad to see that. So sounds like we're all consensus. That's a relatively easy section. You got a good 10 minutes or so still left in class, 15 maybe even. So yes, you should be starting on this. There's no reason to waste 15 minutes of your life. Get started on 9.3 or be finishing up 9.2. That's acceptable as well, but be doing something productive. Have a great weekend, everybody.